Now I'm going to walk quite slowly and I'm going to measure time. And I will start to measure the time here at the origin now. And arriving here at the 5 meters mark, time is 6 seconds. Here at the 10 meters mark, time is 13 seconds. Here at the 15 mark, time is 19 seconds. Here at 20 meters, time is 26 seconds. And the last data is scattered 25 meters, the time is 32 seconds.
All the data is in the table, with the first column highlighted in yellow and marked with the symbol for the physical quantity of time, t. Below it, in square brackets, is the unit of time, s, indicating that time is measured in seconds. In the second column, the symbol for the quantity is now x, indicating that movement is along the x-axis in a straight line. And below that, in square brackets, is the unit of measurement for position, which is meters. Next, we begin constructing a graphical model by first drawing the coordinate system. In this system, the horizontal axis represents time and the vertical axis represents position. The time axis is marked in intervals of 2 seconds, extending up to 34 seconds. We extend slightly beyond the last measured time data point, which was 32 seconds, to ensure all data points fit within our coordinate system. It's important to note that the interval on the axis doesn't always have to be 1, it can also be 2, or for example 5. On the position axis, the interval is also set at 2 meters. However, it could also be 5 or 10. The horizontal and vertical axes do not need to have the same interval as long as the interval on each axis remains consistent. We start plotting data points on the coordinate system. The first row's data value is 6 seconds for time, which is taken from the horizontal time axis, and the first data value for position is 5 meters from the vertical position axis. Each row is plotted as a point on the coordinate system. Remember, time values are taken from the horizontal axis and position values from the vertical axis. Once all data points are plotted, we notice they align quite well with a straight line. Therefore, we fit a line through these points, ensuring that there are roughly equal numbers of points above and below the line, positioning it as centrally as possible among the data points. We select 2 points from the line, marked in yellow, and complete a right triangle in the coordinate system. The subscripts 1 and 2 indicate 2 different time values, so they must be distinguished with different subscripts, as well as the position subscripts since 2 different position values are involved. When using the graphical model, these points must be selected from our graphical model, so from the line and not directly from the data points. To find the slope, we need to know the lengths of the legs of the right triangle on the time and position axes. Hence, we use curly braces and the formulas delta t and delta x. Delta indicates a change, so on the time axis, we calculate the change in time as t2 minus t1, and on the position axis, we calculate the change in position as x2 minus x1. These represent the lengths of the legs of the right triangle. We proceed to calculate the slope of the line, which is delta x divided by delta t. We substitute the formulas and then the numerical values visible in the figure. 22 meters for x2 and 8 meters for x1 and 28 seconds for t2 and 10 seconds for t1. Simplifying the numerator and denominator, we get a result of 0.8 meters per second. This unit indicates that we have calculated the velocity. Therefore, we can now state that the physical interpretation of the slope is velocity. In physics applications, this velocity is referred to as the physical slope. We have thus successfully derived the physics formula for velocity, which is equal to the change in position divided by the change in time. Zooming in closer to the origin, the 0.0 point in the coordinate system, we see the time and position axes with an interval of 1. Let's examine what the slope actually means graphically. the change in position is 0.8 meters, and the change in time is 1 second. Graphically, this means that for every 1 second increment on the time axis, the position changes by 0.8 meters in the positive direction. The yellow arrow represents a 1 second interval, so moving 1 second forward in time results in a 0.8 meter change in position towards positive direction. Continuing this movement forms the straight line. The slope of the line indicates how steeply the line increases and, in some cases, decreases. We write down the mathematical formula for velocity and mark the green points on the line. These green points move along the line, demonstrating that velocity can be calculated using any 2 points on the line. It doesn't matter which 2 points are chosen because the slope of the line remains constant. The points can also be in different order. If the second point is chosen on the left and the first point on the right, the same formula still applies.